Hello, this is AQA A-Level Chemistry. It's the Year 12 topic, bonding, and this is video number 8. In this, we're going to revisit a lot of the key principles once again about the properties of different bonding types or compounds of different bonding types. So, as always, I'm going to recommend that you pause as you go, have a go at answering the questions for yourselves or try and get out the activities, and then check your answers once you've given it a go. You'll get to see what's gone well, and you'll get to see what might need to be developed a little further. So we're going to start off by looking at the objectives here, and you can see there's lots here about enthalpy of vaporization. We're looking at enthalpy changes when things melt or boil, etc. And we're going to remind ourselves about the 3 types of bonds, and we're also going to revisit intermolecular forces. Question at the bottom here for you to try. And so the question is, when is the only circumstance that a particle would have no kinetic energy? And that would be at absolute zero. Now, when we say absolute zero, what we mean by that is 0 Kelvin. That will be the point at which all activity stops. And we work in Kelvin, but we also work in Celsius, so we can also put this down as negative 273 degrees Celsius. So have a think about these. This is actually something you will have learnt about many, many years ago. And I'm not going to write down any evidence here, but we will take a look and discuss the evidence for them. So in terms of arrangement of particles, in a solid, it's a regular structure. In liquids and gases, it is random. Now, what evidence we have for that is that liquids and gases flow. So if we can see that the particles are able to move randomly, they're not in a fixed position vibrating around it, you can see that quite clearly. If we then think about the spacing, when a solid, they're very close together. In a liquid, they're also very close together. But in a gas, the particles are much further apart. You may well, when you were younger, have done a little experiment with this where you had 3 syringes, one with sand, one with water, and one with gas. You seal at the end and you try to push in the plunger. The only one that you can do that with is a gas. You can't squash the solid or the liquid. And then the movement of particles. Well, in a solid, the particles vibrate around a fixed point. In terms of liquids, they're moving around rapidly. Again, we get to see that where water flows over each other. That's the particles slipping and sliding over each other. And in a gas, it is rapid movement. And we know that that exerts pressure as particles move around within a container and make collisions with the inside of the container. So now let's take a look at energy changes on heating. Have a think about these questions. So particles in a solid are vibrating about a fixed point. If I provide more heat energy, what will happen? Well, the vibrations will get bigger and the particles will move slightly further apart. So we're still very close together, but we are going to get that expansion. And you may recognise the apparatus that I've put on here from physics lower down in school, or perhaps even in chemistry or Key Stage 3 science anyway, where you have the ball that fits snugly through the socket, but if you heat the ball, it no longer fits through. That expansion is evidence that the particles are moving slightly further apart. So, more questions for you to consider. If more energy is provided, what happens to the regular structure of the solid? Well, the regular structure does start to break down. We're talking about beyond the expansion of that ball in the experiment I spoke about. We're talking about ice getting more energy provided. The particles start to vibrate more and more until eventually there's a less strong attraction between them, so they can move slightly further apart but also over each other. Key differences between particles in material before and after they have melted. So they are slightly further apart, as we've already discussed, and they're able to move around more. They're less strongly attracted to each other. Now, if we think about heating a liquid, have a go at these. So if more heat is provided, what happens to the speed of the particles? Well, particles start to move faster. It will increase because there will be more kinetic energy within there. And what will happen to the distance between the particles? Well, again, as things get hotter, the particles do get further apart. And in a gas, we know the particles are much further apart. A couple of questions here about liquid turning into gas. So, what is the key difference between particles in a liquid and a gas with respect to speed? Well, it will be faster in a gas. What will be the difference in relation to distance? We're covering a lot of similar themes here. We've already discussed them. They'll be much further apart in a gas. And we call that the enthalpy change of vaporization. We're now going to take a look at some more questions and an explanation of why we see the curve that we see. It says melting point curve, but we've got melting and boiling shown here. The bottom section wants to know, why does it flatten? So let's take a look at the answers. If a gas is provided with more thermal energy, what happens to the kinetic energy of the particles? Well, it increases. And what will happen to the distance? We're repeating ourselves here, but it is important. It increases. So when we look at this graph and we've got the pink section and the green section, it flattens off. Why? Because we are still providing more energy. More energy is going into it. Well, the temperature does stay the same during the process of melting and boiling from when you get the start of your melting. And if you've ever done a melting point curve, you will know we get a range from when we see the first evidence of melting beginning until the last crystal has melted. But the internal energy does carry on increasing. It's just that the extra energy that's going in is being used to break bonds, to overcome forces of attraction, rather than add to the kinetic energy and add to what's going to lead to a higher temperature. Going to take a look to finish off on this video at crystals, and we're going to look at some different types of crystals. So a good opportunity for some reminders actually of the key properties of different structure types. Have a go at these questions. So what type of force holds together an ionic crystal? It's electrostatic forces between oppositely charged ions. Melting point, high or low? High. Why is it high? Because there are lots of strong electrostatic forces between oppositely charged ions, all really important to include. And therefore lots of energy is needed to overcome them. Now, you may be asked to draw a sample of NaCl, and I would always stick to a similar format. Sometimes you will be guided to draw it in this format, but if not, I would come back to it anyway. So I'm going to start off with my positive and negative ions in a two-dimensional plane, and I'm then going to turn it into three-dimensional by creating a cube. You can see the pluses are surrounded by minuses, the minus is surrounded by pluses. I've got my ionic structure shown clearly. The plus is the Na plus, the minus is the Cl minus. Let's move on to metallic crystals. Have a go at these questions. So what type of force holds them together? Well, it's electrostatic forces again. Do they have high or low melting points? Metals have high melting points. High, why? Now this time it is because of the electrostatic forces again, but we have a subtle difference in the explanation compared to ionic. There are lots of strong electrostatic forces, not between oppositely charged ions now, but between positive ions and delocalized electrons. And therefore lots of energy is needed to overcome them. So how might you draw a sample of Na? Again, I'm going to recommend you stick to this similar format if you're ever asked to draw them. Questions will often specify you need to draw 8 of the ions, and you need to show it's a regular structure. So that's what I've shown there. Occasionally you might need to include electrons. For that you would need to remember that each sodium atom has 1 delocalized electron. So this would be matched with 8 electrons through the structure. And finally, molecular crystals. So I'm going to give a specific example of this later on, but there are molecular crystals that you are familiar with. Have a go at answering these. So these are held together by intermolecular forces, and that means the melting points are low. Why does it mean they're low? Intermolecular forces are weak. Hydrogen bond is around 1/10 of the strength of a covalent bond. Dipole-dipole forces are around 1/10 of the strength of a hydrogen bond. Van der Waals are around 1/10 of the strength of a dipole-dipole. So weak intermolecular forces, so not much energy is needed to overcome. Now, one prime example of this is iodine crystals. You can see here my iodine is blue-black solid. It's turning into a purple vapour. But actually, we're seeing that it's very quickly going back to solid crystals once we get away from the heat. We're only heating that very gently. Now, how would we draw that I2 crystal? This looks quite complicated, but we are following a similar pattern to what we saw with ionic. I've got my I2 molecules, and they are in a regular structure. It's a regular structure because it's a crystal. But the green dotted lines here are representing Van der Waals forces. I2 is not a permanent dipole, so the strongest intermolecular force here has to be Van der Waals forces. Now, because they're weak, that's why iodine will sublime at a relatively low temperature with very little heat energy needing to be added. Just as background, subliming is where we go from a solid directly to a gas and we bypass the liquid phase. And that's something that we see with iodine crystals. That takes us to the end of this video. Thank you for listening. Goodbye.